Hey guys, it's Murat Duman here. As I said at the end of the second video, I'm continuing to solve problems about modeling problems by using differential equations. Our differential equation is given in this form, and y0 is equal to y sub 0 part A, k is equal to 0.2, and we are asked to plot y versus t for several values of y sub 0 between 0.5 and 1. Part B, we are asked to estimate the critical initial population y sub c below which the population will become extinct. Part C, we are asked to choose other values of k and find the corresponding y sub c for each one and plot y sub c versus k. First things first, let's find the integrating factor. Integrating factor is equal to e to the minus integral 1 plus sine t over 5 dt, and it's equal to e to the cosine t minus t over 5. I will skip the integration part. After integration part we will get y e to the cosine t minus t over 5 is equal to minus k integral e to the cosine t minus t over 5 dt plus c. And from here y is equal to minus k integral e to the cosine t minus t over 5 dt plus c times e to the t minus cosine t over 5. And in order to find the constant c, we will use the initial condition, which is y0 is equal to y sub 0, and it's equal minus k times c times e to the minus 0.2, and from here c is equal to minus y0 times e to the 0.2 over k. And I will use the value of the constant c in the equation again, and y is equal to minus k integral e to the cosine t minus t over 5 dt minus y0 e to the 0.2 over k times e to the t minus cosine t over 5. As far as I know, there is no analytical way to calculate this integral, so I will calculate the value of this integral by using MATLAB, and for k is equal to 0.2, I will plot y versus t for several values of y sub 0 between 0.5 and 1. And in this graph we see the solution for different y0 values where k is equal to 0.2. In this graph, blue color represents the solution for y sub 0 is equal to 0.5, and the black color represents the solution for y sub 0 is equal to 0.6, and so on and so forth. As you see, for relatively small y sub 0 values, which represents the initial population, the population tends to become extinct. Because, as you see, sooner or later the value of y goes under 0. And this was the part A. What about B? In part B, we are asked to estimate the critical initial population y sub c below which the population will become extinct. As you see, the critical population under which the population become extinct is somewhere in this area, and it's closer to the green colored line, which represents the y sub 0 is equal to 0.8. By using the proper numerical calculation, you will see that critical y value is roughly equal to 0.83 for k is equal to 0.2. And in part C, we are asked to choose other values of k and find the corresponding y critical values for each one and plot y critical versus k. And again, with the proper numerical calculations, for k is equal to 0.1, the corresponding y critical value is roughly equal to 0.42. And for k is equal to 0.2, y critical value is roughly equal to 0.83. For k is equal to 0.3, y critical is equal to 1.25. For k is equal to 0.4, y critical value is equal to 1.67, and for k is equal to 0.5, y critical value is roughly equal to 2.08. And as you see, there is a linear relationship between the k values and the corresponding y critical values. And let's plot the y critical values versus k values by using MATLAB. This is the graph for y0 versus k, and clearly you see the linear relationship between y sub 0 and k. And this is the end of this problem. New question. The temperature of an object changes at a rate proportional to the difference between its temperature and that of its surroundings. A cup of coffee has a temperature of 200 degrees Fahrenheit when freshly poured, and 1 minute later has cooled to 190 degrees Fahrenheit in a room at a 70 degrees Fahrenheit. Determine when the coffee reaches a temperature of 150 degrees Fahrenheit. First of all, the temperature of an object changes at a rate proportional to the difference between its temperature and that of its surroundings. So, this is our coffee, and this is its surroundings. And this is the temperature scale of the coffee and its surroundings. Initial temperature of the coffee is 200 degrees Fahrenheit, and the temperature of its surroundings is 70 degrees Fahrenheit. 1 minute later, the coffee has cooled to 190 degrees Fahrenheit. And we are asked to find when the coffee reaches a temperature of 150 degrees Fahrenheit. Q of T is the current temperature of the coffee. General form of our differential equation is dq over dt is equal to rate in minus rate out. There is nothing around to increase the temperature of the coffee, so the rate in will be 0. Since the temperature of its surroundings is lower than the temperature of the coffee, it will be cooled in time, and the temperature of the coffee will be decreasing proportional to the difference between its temperature and its surroundings. So our differential equation is dq over dt is equal to minus k times q minus 70. And this part is the difference in temperature. So our differential equation is dq over dt plus k times q is equal to 70k. Since I have solved many differential equations in this form, I will directly write q, and q is equal to 70 plus c, the constant, times e to the minus kt. I will use the initial value in order to find the constant c, and our initial value of q is equal to 200, and from here our constant c is equal to 130. So our differential equation is q is equal to 70 plus 130 times e to the minus kt. We will use the extra given information to find this k value. which is Q of 1 is equal to 190 degrees Fahrenheit. So 190 is equal to 70 plus 130 e to the minus k, and from here k is roughly equal to 0.08. We are asked to find when the coffee reaches a temperature of 150 degrees Fahrenheit, so 150 is equal to 70 plus 130 e to the minus 0.08 times t. And from this equation, t will be found as roughly equal to 6.07 minutes. Ninth problem. A rocket is launched straight up from the surface of the Earth with initial velocity v0 is equal to root square 2gr, where r is the radius of the Earth and is equal to 4,000 miles. Neglect air resistance. Find the time required for the rocket to go 240,000 miles. The solution of this problem is very similar to the first problem, which was a rocket problem too. However, I chose this problem for a particular reason, and you will understand the reason during the solution. This is Earth and its radius r. This is the positive x direction, and our rocket can be anywhere on the x direction. And this is the gravitational force, F gravity, and it's towards the Earth, so it's on the minus x direction. Since there is no air friction, we will be just dealing with F gravity. So, force is equal to mass times acceleration, which is equal to m times dv over dt. As I said, we are just dealing with the gravitational force in this question, and the gravitational force is inversely proportional to the distance squared, so m dv over dt is equal to some constant k over distance square, which is equal to r plus x square here, since we are calculating the distance from the center of the Earth. Since gravitational force is towards to the Earth, there will be a minus sign here. In order to find the constant k, we will use the initial condition. On the surface of the Earth, F gravity is equal to minus m times g, and it is equal to minus k over r square. And from here, k is equal to mg r square. And let's use the constant k in our differential equation. M dv over dt is equal to minus mg r square over r plus x squared. There are three variables here. First one is the velocity, second one is the time, and third one is the distance. Let's eliminate one of those variables. dv over dt is equal to dv over dx times dx over dt, and is equal to minus gr square over r plus x square. dx over dt is equal to v, so v dv over dx is equal to minus gr square over r plus x square. And the solution of this differential equation is v square over 2 is equal to gr square over r plus x plus the constant c. In order to find the constant c, let's use the initial condition, which is v0 is equal to root square 2gr. v0 square over 2 is equal to gr, and it is equal to gr plus c, and from here c is equal to 0. So v square over 2 is equal to gr square over r plus x. And from here v is equal to root square 2g r square over r plus x. And here it comes to the point where I would like to emphasize. Let's look at the unit of v. unit of v is equal to root square of g, which is meter per second square, times r square, which is miles square, over r plus x, which is miles. There will be a cancellation here, and unit of v is equal to root square meter times miles over second. And as you see, the unit of velocity is neither meter per second nor mile per second here. But since we are dealing with big distances in this question, it will be wise to choose the unit of velocity as miles per second. 1 mile is roughly equal to 1609 meters. So if we divide this equation by root square of 1609, we will get the unit of velocity as mile per second. So let's update our equation for velocity. Velocity is equal to root square of 2g r square over 1609 times 1 over root square of r plus x. This term is already a constant and it is roughly equal to 441.5. So velocity is equal to 441.5 times 1 over root square r plus x. We are asked to find the time required for the rocket to go some distance, so our equation should contain the variable time. So v is equal to dx over dt, and it's equal to 441.5 times r plus x to the minus 1 over 2. And from here, dx is equal to 441.5 times r plus x to the minus 1 over 2 dt. And from here, r plus x to the 1 over 2 dx is equal to 441.5 times dt. And if you solve this easy integral, you will get in order to find the constant c, let's use the initial condition. And from here, c is equal to 1686.50. Let's update our equation by using this constant. 2 over 3 times r plus x over 3 over 2 is equal to 441.5 times t plus 1686.50. Here r is equal to 4000 and x is equal to 240,000. So our equation is and if you solve this equation, you will see that t is roughly equal to 50.45 hours. This is the end of the problem, and we are finished with modeling problems by using first order differential equations. Now we will study existence and uniqueness of the solutions of first order linear and nonlinear differential equations. We will study two theorems. The first one is about the existence and uniqueness of the solutions of first order linear differential equations, and the second one is about the existence and uniqueness of the solutions of first order nonlinear differential equations. And let's study the first theorem. If the functions p and g are continuous on an open interval I in which t is between alpha and beta, containing the point t is equal to t sub 0, then there exists a unique function y is equal to phi of t that satisfies the differential equation y prime plus p of t times y is equal to g of t for each t in I, and also satisfy the initial condition y t sub 0 is equal to y sub 0, where y sub 0 is an arbitrary prescribed initial value. Let's repeat what we read. We have a first-order linear differential equation, and our functions p and g are continuous on an open interval I, in which our independent variable t is between alpha and beta, containing the point t is equal to t sub 0. Under these conditions, there exists a unique function y which satisfies our differential equation, and also it satisfies our initial condition. So, if the conditions in this theorem are satisfied by our differential equation, then it is guaranteed that we have a solution, and this solution is unique. Let's write it down. This theorem states that the given initial value problem has a solution, which is the definition of existence. And also, it states that the problem has only one solution, which is the definition of uniqueness. In addition, it states that the solution exists throughout any interval I containing the initial point t sub 0 in which the coefficients p and g are continuous. Let's solve an example. Our initial value problem is given in this form, and we are asked to use the Theorem 2.4.1 to find an interval in which this initial value problem has a unique solution. Let's write the differential equation again. Here, p of t is equal to 2 over t and g of t is equal to 4t. As you see, g of t is continuous everywhere, but p of t is continuous where t is bigger than 0 or t is smaller than 0. And the interval where t is bigger than 0 contains the point 1 where the initial value is defined. So the interval of the solution is the region where t is bigger than 0. Indeed, the solution of this problem is y is equal to t squared plus 1 over t squared, where t is bigger than 0. And as you see, the solution is discontinuous where t is equal to 0. And this is consistent with what the theorem says about the interval of the solution. And let's write it down. the solution is discontinuous where t is equal to 0. For nonlinear differential equations, we must replace Theorem 2.4.1 by a more general theorem, such as the following. Theorem 2.4.2. Let the functions f and df over dy be continuous in some rectangle. T is between alpha and beta and y is between gamma and sigma, containing the point t sub 0, y sub 0, then in some interval in which t is between t sub 0 minus h and t sub 0 plus h, where t is between alpha and beta, there is a unique solution. Y is equal to phi of t of the initial value problem, where y prime is equal to f of t y and y of t sub 0 is equal to y sub 0. Let's repeat what we read. Y prime in our first order nonlinear differential equation is equal to function f, and f is the function of independent variable t and dependent variable y, and our initial value is defined at the point where t is equal to t sub 0. If the functions f and df over dy are continuous in some rectangle containing the initial value, then in some interval there is a unique solution between t sub 0 minus h and t sub 0 plus h. Let's write what we said. The conditions stated in this theorem are sufficient to guarantee the existence of a unique solution of the initial value problem in some interval between t sub 0 minus h and t sub 0 plus h, and the existence of a solution can be established on the basis of the continuity of f alone. It means if f is a continuous function, then definitely the solution exists, but we cannot guarantee whether it is a unique solution or not. And let's solve some examples. Example 2. Apply Theorem 2.4.2 to the initial value problem given in this form. To apply Theorem 2.4.2, we will look at f of xy and df of xy over dy. Let's check fxy and dfxy over dy. F of xy is equal to 3x squared plus 4x plus 2 over 2y minus 1, and dfxy over dy is equal to minus 3x squared plus 4x plus 2 over 2y minus 1 square. Both of the functions are continuous everywhere except on the line y is equal to 1. Let's write it down. Both of the functions are continuous everywhere except on the line y is equal to 1. Consequently, a rectangle can be drawn about the initial point 0, -1 in which both f and df over dy are continuous. Let's write it down. Consequently, a rectangle can be drawn about the initial point 0, -1 in which both f and df over dy are continuous. Therefore, Theorem 2.4.2 guarantees that the initial value problem has a unique solution in some interval about x is equal to 0. This is our initial value. This is y is equal to 1 line on which f and df over dy are discontinuous. Now the question is, can we stretch solution infinitely far in both the positive and negative x directions? Can we stretch the solution infinitely far in both the positive x and minus x directions? And the answer comes from the solution. Then let's solve this problem. 2y minus 1 dy is equal to 3x squared plus 4x plus 2, and y of 0 is equal to minus 1. And y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus the constant c. In order to find the constant c, we will use the initial value, and from the initial value, which is y of 0 is equal to minus 1, we get c is equal to 3. So y minus 1 squared is equal to x cubed plus 2x squared plus 2x plus 4, and from here y is equal to 1 plus or minus root square x cubed plus 2x squared plus 2x plus 4. Since y of 0 is equal to minus 1, y is equal to 1 minus root square x cubed plus 2x squared plus 2x plus 4. This term must be positive in order to keep the solution real. So x cubed plus 2x squared plus 2x plus 4 must be bigger than 0. So x must be bigger than minus 2. And as I said before, the answer comes from the solution, and which is x is bigger than minus 2. So let's sketch the graph again. This is the x is equal to minus 2 line. And this is the rectangle that we can draw about the initial point. And as you see, we can stretch infinitely far in positive x and minus y directions. So this is our rectangle for the solution. Example 3. Consider the initial value problem. Y prime is equal to y to the 1 over 3 and y of 0 is equal to 0 for t is equal or bigger than 0. Apply theorem 2.4.2 to this initial value problem and then solve the problem. F of t comma y is equal to y to the 1 over 3 is continuous everywhere. But df over dy is equal to 1 over 3 times 1 over y over 2 over 3 is not continuous when y is equal to 0. So, in terms of applying Theorem 2.4.2, we cannot look for an interval where f and df over dy is continuous, because the initial value is on the line where df over dy is discontinuous. Thus, Theorem 2.4.2 does not apply to this problem, and no conclusion can be drawn from it. The continuity of f assures the existence of solutions but not their uniqueness. To understand the situation more clearly, we must actually solve it. And let's solve the problem. Y over minus 1 over 3 dy is equal to dt. 3 over 2 y over 2 over 3 is equal to t plus the constant c. So y is equal to 2 over 3 times t plus c over 3 over 2. And the initial condition is satisfied if c is equal to 0. So y is equal to, let's call this solution phi1. Phi1 of t is equal to 2 over 3 times t over 3 over 2, where t is equal or bigger than 0. On the other hand, y is equal to phi 2 of t is equal to minus 2 over 3 times t over 3 over 2, and t is equal or bigger than 0, is also a solution of the initial value problem. Moreover, the function y is equal to, let's call the solution psi of t is equal to 0 for t is equal or bigger than 0 is yet another solution. In order to generalize the solutions, for arbitrary t sub 0, the functions y is equal to, let's say, chi of t is equal to 0 if 0 is equal or smaller than t and t is equal or smaller than t sub 0, and plus or minus 2 over 3 t minus t sub 0 over 3 over 2 if t is equal or bigger than 0. If you check these solutions, you will see that these solutions satisfy the initial value problem. These solutions are continuous differentiable and are solutions of the initial value problem. And here on this graph we see the solutions y is equal to 0 and all other solutions for different values of t sub 0. Example 4. Solve the initial value problem y prime is equal to y square and y of 0 is equal to 1 and determine the interval in which the solution exists. Since this differential equation is nonlinear, we will look at Theorem 2.4.2 and f of t comma y is equal to y square and df over dy is equal to 2y. Since both f and df over dy is continuous, Theorem 2.4.2 guarantees that this problem has a unique solution. And let's look at the solution. Y to the minus 2 dy is equal to dt. So minus y to the minus 1 is equal to t plus the constant c and y is equal to minus 1 over t plus c. C is equal to minus 1 in order to satisfy the initial condition. So y is equal to 1 over 1 minus t is the solution of the given initial value problem. Clearly, the solution becomes unbounded as t goes to 1. Therefore, the solution exists only in the interval minus infinity is smaller than t and t is smaller than 1. Because in this interval our function is continuous and also this interval contains the initial value. Sometimes it is possible to solve a nonlinear equation by making a change of the dependent variable that converts it into a linear equation. Let's write it down. Sometimes it is possible to convert a nonlinear equation into a linear equation by making a change of the dependent variable. The most important such equation has the form y prime plus p of t times y is equal to q of t times y to the n. Let's call it star equation. Let v is equal to y to the 1 minus n. This is the change of the dependent variable that we need to convert nonlinear equation into linear equation. So dv over dt is equal to 1 minus n times y to the minus n times dy over dt, and dy over dt is equal to 1 over 1 minus n times y to the n times dv over dt. Substituting this into the equation star, we get y to the n over 1 minus n times dv over dt plus p of t times y is equal to q of t times y to the n. And from here, p prime plus 1 minus n times p of t times y to the 1 minus n is equal to 1 minus n times q of t. Setting v is equal to y to the 1 minus n, we get v prime plus 1 minus n p of t times v is equal to 1 minus n times q of t. And this is a linear equation. So we converted a nonlinear equation into a linear equation by making a change of the dependent variable. And that's what Bernoulli equation is. And let's solve an example. And before solving the example 5, here I wrote what we have found in the previous slide, and that is how to convert a nonlinear equation, which is in the form of Bernoulli equation, into a linear equation by making a change of the dependent variable. And here our example 5. In this example we are asked to solve the given differential equation, which is y prime plus 2 over t times y is equal to 1 over t squared times y cubed. This differential equation is in the form of Bernoulli equation, and here p of t is equal to 2 over t and q of t is equal to 1 over t squared, and n is equal to 3 here. Let's write it down. P of t is equal to 2 over t, q of t is equal to 1 over t squared, and n is equal to 3 here. So v is equal to y to the minus 2. Let's write the final linear differential equation. V prime plus 1 minus 3 times 2 over t times v is equal to 1 minus 3 times 1 over t squared. And here v prime minus 4 over t times v is equal to minus 2 over t squared. And here we get a linear differential equation. And in this linear differential equation, our integration factor is equal to e to the minus 4 integral dt over t. So our integration factor is equal to t to the minus 4. By multiplying both sides by this integration factor, we get v prime over t to the 4 minus 4 over t to the 5 times v is equal to minus 2 over t to the 6. And from here, v times t to the minus 4 prime is equal to minus 2 over t to the 6. By integrating both sides, we get v times t to the minus 4 is equal to 2 over 5 t to the minus 5 plus the constant c. And from here, v is equal to 2 plus 5c t to the 5 over 5t. And v is equal to y to the minus 2, so from here y is equal to plus or minus 5t over 2 plus 5c t to the 5 to the 1 over 2. And this is the solution. Let's talk about discontinuous coefficients. Linear differential equations sometimes occur in which one or both of the functions p and g have jump discontinuities. If t sub 0 is such a point of discontinuity, then it is necessary to solve the equation separately for t is smaller than t sub 0 or t is bigger than t sub 0. Afterward, the two solutions are matched so that y is continuous at t sub 0. This is accomplished by a proper choice of the arbitrary constants. And let's solve an example in order to understand this more clearly. Example 6. Solve the initial value problem, which is y prime plus 2y is equal to g of t, where y of 0 is equal to 0, where g of t is equal to 1 when t is between 0 and 1, and g of t is equal to 0 when t is bigger than 1. As you see, there is a jump discontinuity in g of t where t is equal to 1. And let's solve this differential equation for the first time interval. Differential equation for the first interval. In the first interval, g of t is equal to 1. So y1 prime plus 2y1 is equal to 1, where y1 of 0 is equal to 0. So y1 times e to the 2t prime is equal to e to the 2t, and from here y1 times e to the 2t is equal to 1 over 2 times e to the 2t plus the constant c, and y1 is equal to 1 over 2 plus c times e to the minus 2, where y1 of 0 is equal to 0, and by using this initial value we will find the constant c. So 0 is equal to 1 over 2 plus c, and from here the constant c is equal to minus 1 over 2. So y1 is equal to 1 over 2 minus 1 over 2 times e to the minus 2t, where t is between 0 and 1. Now we can solve for the second interval, where g of t is equal to 0, so y2 prime plus 2y2 is equal to 0, and y2 times e to the 2t prime is equal to 0, so y2 times e to the 2t is equal to the constant c. So y2 is equal to c times e to the minus 2t, where t is bigger than 1. And here we solved the differential equation separately for the two time intervals, which are separated by the jump discontinuity, which occurs at t is equal to 1. And the critical part here is the solution y of the original initial value problem must be continuous, since its derivative must exist, and we need the constant c in y2 so that y2 at t is equal to 1 has the same value as y1 at t is equal to 1. Thus y2, which is c times e to the minus 2t, must be equal to y1, which is 1 over 2 minus 1 over 2 times e to the minus 2t at t is equal to 1. So c times e to the minus 2 is equal to 1 over 2 minus 1 over 2 times e to the minus 2, and from here c is equal to 1 over 2 times e to the 2 minus 1. So we have a partial solution for the two-time interval, and we eliminated the jump discontinuity. Let's write the partial solution that we found. Y is equal to 1 over 2 minus 1 over 2 times e to the minus 2t, where t is between 0 and 1, and y is equal to 1 over 2 times e to the 2 minus 1 times e to the minus 2t, where t is bigger than 1. And now let's see the solution and the derivative of the solution on the graph. And as you see, for the solution we eliminated the jump discontinuity at t is equal to 1, but there is still discontinuity for the derivative of the solution where t is equal to 1, and let's write this as a note. For the solution we eliminated the jump discontinuity at t is equal to 1, but there is still jump discontinuity For the derivative of the solution, at t is equal to 1. We are finished with differences between linear and nonlinear equations. For the next video, I'll continue with autonomous equations and population dynamics. If you like this video, don't forget to subscribe. See you!